Hello, can you hear? Can someone reply? Hello,
Yes, sir. We can hear, sir.
hello. Hello, can you hear me? Okay, thank you. Like we are starting the first section of uh, previous year gate question solving. Like I am Suraj P from Chemical Engineering Department. I am solving here fluid mechanics question asked in the year 2017. So, like, can you see the slide? Hello.
Yes, sir. We can see your slide.
Like, if it is possible, please type in the chat box. I'm not like, please unmute yourself. You are not, you are muted yourself. So please unmute. So the question is, an oil is being delivered at a steady flow rate through a circular pipe whose radius is 1.25 into 10 to the power minus 2 meter and the length is 10 meter. The pressure drop across the pipe is 500 pascal. So we are asked to calculate the shear stress at the pipe wall, and it should be in the two decimal places. So we know that shear stress and pressure drop for a circular pipe is related by one equation. Like, uh, if this is the circular pipe, can you see what I have drawn here? Hello.
Yes, sir. We can see, sir.
This is the circular pipe with length L and the pressure at the starting point inlet is P1 and at the outlet is P2. So if we need to calculate the shear stress which is bounded in the wall of the circular pipe. So shear stress will be bounded in this area like in the wall of the circular pipe. So that is related to the pressure drop by the equation. If tau is the shear stress, tau is related to pressure drop as tau is equal to delta P by 2L times radius. So here pressure drop is 500 pascal and the radius is 1.25 into 10 to the power minus 2. So after substituting we will be getting the answer as 0.312 pascal. So like uh, so we need to see how this equation is derived. For that we need to consider a elemental area in a circular pipe. So I am drawing here the elemental section of the circular pipe. So this is the central axis. The elemental thickness is delta x, and the radius of the whole pipe is capital R. The pressure at the starting point is x, P at x, and the ending point is P at x plus delta x. So from the momentum balance, we are aware that sum of forces acting on the control volume will be equal to the difference of rate of momentum out minus rate of momentum in. So here we are calculating the sum of forces in that elemental section. So like force will be equal to the pressure in that section times area of that section. So here there are two sections, like one is P at x plus delta x, and the other one is P at x. So if we need to find the force in these two areas, we can multiply the cross sectional area of these two ends. So it will be coming as so this will be the sum of forces acting on the control volume. So this will be balanced by the shear force. So the shear force will be acting in the walls of the circular pipe. So like this highlighted area, here the shear stress will be counterbalance for that pressure force. The pressure force will be acting in this both ends of the circular tube. So here the pressure force will act, that will be calculated as P into A, and the shear force will be acting in this wall area, and that will be calculated as tau into area. So this is the shear force, where tau is the shear stress. So we need to do a shear stress balance in this elemental area. So if tau Rx is the shear force acting in the uh, radial direction, it will be the net shear force will be equal to he two tau Rx into 2 pi r delta x. Here the area in the case of pressure is calculated as cross sectional area of tube, but the area in the case of shear stress is calculated as circumference of the is calculated as the circumferential area of the tube wall. So the circumferential area of the tube wall will be coming as 2 pi r into delta x, whereas the cross sectional area of the tube is coming as 2 pi r into delta r. So like this is the main difference. In case of uh, pressure force, the circumferential area is 2 pi r into delta r. Whereas in the case of shear force, the circumferential area is 2 pi r into delta x. In case of pressure, we are calculating the cross sectional area, but in the case of shear stress, we are calculating the circumferential area. So the net shear stress will be equal to so like we need to equate these shear force and pressure force. So after equating, we'll be getting after equating and balancing, we'll be getting the in the form of a differential equation. So after this, we need to integrate this equation. So after integrating and putting the boundary condition, we'll be getting so this is the uh, final equation which is relating the wall shear stress with the pressure drop in a circular pipe. So this equation we need to remember. Um, so I have one question. Like if we have two pipes, uh, both are having same length and both have the same diameter also. Uh, but the only difference is here the viscosity of the fluid is flowing fluid is mu, and in case of the second pipe the viscosity is 100 mu. So this is pipe 1, this is pipe 2. Can you tell in which case the shear stress will be more? This is a flowing, both are flowing fluid. So in which case the shear stress will be more?
Sir, pipe 2, sir.
So can anyone tell this? Like if you can comment in the comment box, it will be better. Everyone is telling pipe 2. but I'm giving some more time, like in the previous slide I have shown the equation, like how the shear stress is related to pressure drop and radius of the pipe. Uh, so like once more the options I can give, like stress in the pipe 1 is greater than stress in pipe 2. So stress in pipe 1 and pipe 2 both are equal. Stress in pipe 1 is less than stress in 2. And the fourth one, like we need to know whether the flow is turbulent or laminar. Uh, so are you um, sticking on to the pipe 2 only? Like is your answer fixed as option C, option 3? Like pipe 2 will give higher, will have higher shear stress. Uh, and this one is also not correct. Like this equation is applicable for both laminar and turbulent. And like we need to know one more thing. Like I'm telling one more thing, that uh, like the flow is here the flow is laminar, because like we are not giving any external force like pump and other things, so the flow will be laminar only. Like unless it is specified that it is accelerating. Here I have been specified that it is accelerating, so we can consider the flow is laminar. Moreover, this equation is applicable only for laminar, uh, and it should be one dimensional, and the flow should be fully developed. So like we need to know what is fully developed. Fully developed flow is a flow in which there is no variation of velocity along the x-axis. So for a laminar flow, the velocity profile is parabolic and there is no variation in the x-axis. So that's a fully developed flow. So this equation is applicable only for one-dimensional steady state laminar fully developed flow. So I am giving the solution of this answer, like from the previous equation, that is like if you can substitute the values and check the shear stress in both cases, that will be better. So I am substituting shear stress for pipe number 1. So let me write it as tau 1. Tau 1 is equal to delta P by 2L into D by 2, and tau 2 is equal to delta P by 2L into D by 2. So from this uh, we can conclude that both the shear stress will be equal. It is independent of viscosity of the fluid. Uh, so please note that the shear stress will be equal in both the cases. It is independent of viscosity. And if we need to if we need to check with the option 4, here nothing is specified like if the flow is laminar or turbulent. If it is not specified, um, like for specifying the turbulent nature, we need to they need to tell that the flow is either accelerated, but it is not given in this statement. So we can assume that the flow is laminar in this case. So finally, we got the answer as the shear stress in both the pipes are same. It is independent of viscosity. So we can move to the next question. Previous question was about pipe flow. Now this question was uh, in the fluid mechanics section only. Like a propeller with diameter 15 meter rotates at 1 rps. To understand the flow around the propeller, a lab scale model is made. Important parameters to study the flow are velocity of propeller tip, which is given as pi into n into d, where d is the diameter and g is the acceleration due to gravity. The lab scale model is 1 by 100 of the size of actual propeller. The rotational speed of lab scale model to the nearest integer should be dash rps. Uh, so here they have given two cases. One is the model, other one is the prototype. So like for large scale application, first we will do it in lab scale model, like that's known as model, and for in the large scale it is called as prototype. So why we are doing like this is because of the economics. Initially we cannot do it in a large scale because a large amount of cost will be required in assembling these things. So first what we'll do is we'll make a model, then we will upgrade into a prototype. So there are mainly uh, certain criteria that we follow when we are upgrading from model to prototype. So like mainly three criteria are followed for upgrading from model to prototype. These are geometric similarity, then kinematic similarity, and dynamic similarity. So what is meant by geometric similarity is that if the ratios of if the ratio of dimension in a system is equal, then it's called geometric similarity. So let us consider two dimensions. So like whose dimension is a in this direction and B in this direction. So what geometric similarity means that the ratio of these two sides, that is A1 by B1, should be equal to A2 by B2. So here this small one is the model and the large one is the prototype. So this is the geometric similarity. So next we need to see what is the kinetic similarity. So kinematic similarity is applicable only for a geometrically similar system. So previous slide we came to know what is geometrically similar system, whose ratio of the dimension of two sides are same. That's a geometrically similar system. So for kinematic similarity, the ratio of kinematic properties such as velocity should be equal to the prototype. For the model, the velocity ratio in the x-axis and y-axis should be equal to the prototype. So let's consider a big pipe whose diameter is d and a small pipe whose diameter is d and the length is L. The length is L. So the small pipe is a model and the big pipe is the prototype. So here we assume the geometric similarity is followed, that is L by D equal to small L by D. Then we need to consider uh, 2 points in the pipe section. This is point number 1 and this is point number 2. So if the velocity in the x-axis divided by velocity in the y-axis at this point, for at the point 1 will be equal to velocity as x by velocity at y for point number 2. It is called as a kinematic similarity. So for following kinematic similarity, the system should follow geometric similarity. So in the previous slide we have seen what is geometric similarity, and in this slide we have seen what is kinematic similarity. For following kinematic similarity, the system should first follow geometric similarity. If the velocity at this point in the x-axis and in the y-axis, so this is the velocity in the x-axis and this is the velocity in the y-axis. So that ratio at this pipe will be equal to that ratio in this model pipe. So the third type of similarity is the dynamic similarity. So for following the dynamic similarity, the ratio of forces should be equal. Means like in fluid mechanics, we mainly consider with four types of forces. Like one is the inertial force, The second one is the viscous force. Third one is the pressure force. And fourth one is gravitational force. Um, so the ratio of these forces should be equal in model and prototype. So suppose let us consider Reynolds number. We know that Reynolds number is the ratio of inertial force and viscous force. So if RE1 is the Reynolds number of model and RE2 is the Reynolds number of prototype, then RE1 should be equal to RE2. Similarly, the other ratio is the Proud number. The Proud number is given by the ratio of inertial force to the gravitational force. And we also know that friction factor concept also. So like friction factor was given by uh, pressure force at the wall divided by the inertial force. So till now we have studied uh, the difference between model and prototype. So model is a small scale, uh, small experimental scale thing, and prototype is a large scale thing. So first we will do experiment and determine the parameters required like velocity, frequency, these things like RPM. What is the RPM of the motor? That things we will find using a model. Then we will use such type of similarities like geometric similarity, kinematic similarity for and dynamic similarity for calculation of the prototype compounds. So here what they have given is the diameter of the prototype. It's given as 15 meter. Then the velocity of the prototype is also given. That is the RPM of the prototype. Then we are asked to find what is the RPM of the lab scale model. So for those who have joined, I am repeating this question. So here in this question, like we are asked to calculate there are two systems given. One is a lab scale model, and the second one is a prototype. So what is the difference between lab scale and prototype? I have already discussed. Lab scale is also called as model. So initially, for implementing a big system, we will calculate the parameters using a lab scale model. Then only we will upgrade into a large scale or prototype model. So for this, some similarities like geometric similarity, kinematic similarity, and dynamic similarity is required for the scale up. So these similarity are needed for scale up of model to prototype. So first I have discussed what is a geometric similarity. So a geometric similarity is a similarity in which the ratio of dimensions of any two dimensions might should be equal. So if we consider two diamonds, one is small and one is large. The small one is the model. So if A1, B1 are the dimension of prototype and A2, B2 are the dimension of the model, then the ratio for scaling up should be equal. Like the ratio A1 by B1 should be equal to A2 by B2. This is called as geometric similarity. Next one is the kinematic similarity. For following the kinematic similarity, the system should follow geometric similarity, which is discussed in previous slide. So in this case, if we consider a flowing fluid in which there should be a flow of fluid uh, for this type of similarity, uh, and if we consider point 1 in the prototype and point 2 in the model, then the ratio of velocity that is in the x-axis and y-axis at point 1, that is prototype, should be equal to ratio of velocity in the x-axis to y-axis for the model. So this is the kinematic similarities. There should be the ratio of the velocity should be constant in model and prototype in the x-axis and y-axis. So next one is the dynamic similarity. So for following dynamic similarity, the previous two similarities should be followed. That is kinematic and geometric. Moreover, uh, the ratio in this case, the ratio of inertial forces, like forces, should be equal. In the previous case, we have dealt with dimensions in the geometric similarity and velocities in the kinematic similarity. In the dynamic similarity, the ratio of forces should be equal. In fluid, we have mainly four types of forces. One is inertial, one is viscous, then pressure and gravitational. Uh, and we'll be converting this in various non-dimensionless formulas like Reynolds number, which is the ratio of inertial force to viscous force. Then we have Froude's number, which is the ratio of inertial to gravitational force, and we have the friction factor, which is pressure force in the wall to the inertial force. Uh, so like we are going to solve this problem. So the parameters of the prototype are given as 15-meter diameter and 1 RPS, which is the rotational speed. Moreover, they have given uh, the lab scale model is 1 by 100th of the size of actual propeller. Like from this we can derive that uh, like diameter of the lab scale propeller will be 1 by 100 that of the prototype. So like prototype diameter we already know. Uh, so, so that will be equal to 0.15 meter. So this statement was given in the question. So now we need to find the frequency or the RPM of the model model. Uh, so we can use either three of these equations, like either Reynolds number, Ford's number, or friction factor. Should use it depend on which parameter we need to calculate. In case of Reynolds number, there is no frequency in this. So we can convert the frequency as pi into n into d. So this statement is already given in the question. The velocity of the propeller tip is pi into n into d. We can also use the ratio of Froude number, like if we know the Froude number is equal to u square by gd, u square by gd. This is Reynolds number and this is Froude number. So which one we should use? Can you please tell which one should we use, Reynolds number or Froude's number? In both the cases, velocity and diameter are given. So like we can use either Re1 equal to Re2 or Fr1 equal to Fr2. So here I am using Froude number, that is u1 by, so we need to substitute this u in here. So u in this equation. So this diameter will be cancelled out, these two diameters. So so from this we can calculate the N2 RPM. So can you please tell what is the value of N2? If someone might have calculated the value of N2. You can write in the comment box. Okay, 100. Okay, 10. So, um, so we are getting 10 RPS. So, if do you have any doubt in this calculation? And if you have any doubt, you can mail me, and we can upload this section in the gate portal of IIT Madras. So up to now we have discussed two questions solved in the gate 17, asked in the gate 17 section. So first one, what's about uh, pressure drop in a circular pipe, and the second one was about um, concept of model and prototype. And if you have any doubt, you can you can comment here. Okay, so uh, for book you can refer either uh, transport phenomena. This book you can refer. Moreover, in McCabe's myth also you can refer. Um, so these two books you can refer. Like if you have any doubt up to till now what I have solved, you can comment here. Actually, I am not audible to you. That's why you are not audible to me. So this one also you should remember. Like uh, this might be coming in like one more question or other thing. Like mm, like if the viscosity is different in two fluid, how the shear stress are related. This type of question might be coming in 1 mark. So I am showing the last problem. This is the last problem. So Gautam, do you have any doubt in this? So in the next week, I will be solving some different questions. Like you can attend at that section from next Monday at the same time, like 6 to 7. Like here, you can try with Reynolds number also. Like you can check with Reynolds number also whether if you get Reynolds number whether you are getting the same result or not. So you can check whether you are getting same result or not. Uh, so for checking that thing, we need to see what all things are mentioned in the question. So in the question, we can see here acceleration due to gravity is mentioned. Here nothing about the fluid property is mentioned, like viscosity and these things are not mentioned. So we need to assume that the Reynolds number and other things are constant.
Could you hear me now, sir?
So here the acceleration due to gravity is given. That's why we are using this Froude number.
Am
But
I
in
audible now,
Reynolds
sir?
number, there is no term for gravitational force. But in question, it is given acceleration due to gravity. That's why. So
Hello,
if you substitute this one, you will get a different answer.
sir. Am I audible?
So here we will be getting 15 square divided by 0.15. Uh, and that value will be very higher than like can you calculate and give the result like 15 square divided by 0.15? What is the value of this? So it is coming 1500. 1500 RPS. So, but we can see in the question the RPS of the prototype is 1 RPM. And from that we can get that it will not be that much variation will not be there between the prototype and model. Only a like in the range of 100 and 10, that low range variation will be there. Moreover, this term is given like acceleration due to gravity, and not nothing about fluid properties mentioned, like viscosity is not mentioned. That's why we are not going for Froude number. And that's why we are going only for Froude number and not for Reynolds number. Okay. So like Rishi have asked to explain it once more. So
Sir, am I actually audible?
so Rishi, in this question, for parameters for prototype and model are given. Like dimensions of prototype is given as 15 meters diameter, and the dimension of the model is given as 1 by 100 of prototype. That will be 0.15 meter, and the rotational speed of so this is the second question. The first question is this one. So while taking this one, where is the, are you there in the this one or that first one or second one? Okay, okay, huh. This one. Yeah. So in this case, like we are asked to calculate the shear stress, and they have given diameter of the pipe and the length of the pipe. So we have considered this pipe, circular pipe, and from textbook result we have got the relation between shear stress and the pressure drop as tau is equal to delta P divided by 2L into R. So pressure, we are actually substituting the pressure drop, that is 500 Pascal, that is delta P, and the length and the radius. We are actually substituting these values in this equation and calculating the shear stress. So one more thing, like um, pressure force will be acting at the end of the pipe, and that will be acting in the cross sectional area. This is the cross sectional area, and the shear stress will be acting in the uh, walls of the pipe. So next section I'll be trying to solve the problem on non-Newtonian. Like if there is some question about non-Newtonian, I can solve that. Like You are from fourth year or third year? Third year BTech. Can you please tell me, you people are from which background? Final year, okay. Huh. All are from final year or okay. So you might have written the in third year also. You might have written third year the gate exam. So have you qualified that? Okay. So have you written it previously? Like Rishi haven't written it. Like anybody have written in the third year? Okay. No, nobody have written. Okay. Okay. I prefer you to go to the previous questions and solve it before the December. Like, uh, like my suggestion is to use to solve all the previous questions. Like you can get it from website. Like from 94 to this 2023. So I can share the Google Drive link also for that. Uh, so if anybody need, you can directly mail me. So if anybody need the previous year questions, you can directly mail me. I'm writing my mail ID here. And I suggest you to solve this previous question. It will be beneficial for you. Like you can mail me. I will share the previous year questions.